Certain theoretical frameworks suggest that the influence of dark energy may not remain constant forever. Over immensely long timescales, the force driving cosmic expansion could gradually weaken, allowing its influence to fade. In the year 2025, the Dark Energy Spectroscopic Instrument, DESI, found that evidence for evolving dark energy has been discovered. Results, when combined with cosmic microwave background data, suggest that the density of dark energy is slowly decreasing with time. The graph depicts this decrease with the orange downward slope. As this happens, the balance of the cosmos may slowly tilt back toward the attractive pull of gravity. If such a transition were to occur, the expansion of the universe would begin to slow. Over vast stretches of time, it could eventually reach a moment of stillness, an equilibrium where expansion halts. Beyond that point, gravity will take the lead, drawing the cosmos inward and ushering the universe into a long and gradual phase of contraction. During the contraction phase, the universe would begin to shrink. Galaxies, stars, and vast clouds of matter would slowly drift closer together as the overall scale of the cosmos diminishes. Distances between cosmic structures would steadily narrow, not because galaxies are rushing through space, but because space itself would be gently drawing inward. As this process continues, the fabric of space-time would grow increasingly compressed and dense, approaching the smallest meaningful scale known in physics, the Planck scale, where the familiar laws of gravity and space-time begin to give way to the deeper rules of quantum gravity. As the universe contracts and approaches the Planck scale, Einstein's equations of general relativity begin to break down, producing strange and unphysical results, most notably infinities, where quantities like energy density and space-time curvature grow without bound. Such infinities signal that the theory has reached the limits of its applicability. Prospective theories of quantum mechanics, such as string theory and loop quantum gravity, attempt to explain the fate of the universe. In these mathematical frameworks, the troubling infinities disappear. The theories suggest that when the universe contracts to its smallest possible size, approaching what is known as the Planck density, the geometry of space-time itself develops a resistance to further collapse. Space-time cannot compress indefinitely. Instead, a profound turning point emerges, the moment when contraction gives way to a renewed phase of expansion. One may picture this through the simple image of compressing a lattice of springs. At first, the lattice compresses easily. As it nears its minimum size, however, it becomes increasingly stiff. Eventually, the compressed springs push back with force, causing the structure to rebound. In loop quantum gravity, the geometry of space-time behaves in a similar way. The fabric of space-time can curve and compress only up to a certain limit. As that limit is approached, the quantum structure of space-time resists further compression, preventing the formation of infinite density and triggering a bounce that sends the universe expanding once again.